Okay, so I reinforced a little bit yesterday in your investigate, but also this is what we started talking about on Friday. We talked a little bit about this earlier this week. We kept talking about that huge number, right? 6.02 times 10 to the 23rd particles. Well, today I want to get into what particles means. When I say particles, what exactly am I talking about? Right? We initially talked about this. We were talking about a mole kind of like a dozen, right? A dozen is 12 of a thing. And when we're talking about a dozen things, we're talking about donuts or roses or books or whatever. But now when we're talking about a mole and we're talking about a giant quantity, well, what exactly are we talking about, right? These are chemistry kinds of things. And none of this is really new. Maybe the newest part on here is formula unit, right? But what formula unit describes is not something new, right? Atoms, we know what atoms are. The smallest indivisible chunk of an element. We know what ions are, something that is missing or has extra electrons to make it charged in some way. Important to note on here, you have something like our polyatomic ions are still ions, right? There's, I think, phosphate listed here as an example. PO4 with a -3. Strontium with a +2. Formula units are the smallest particle of an ionically bonded compound. So again, that's something we've been doing a lot with. That's lithium bromide, that's iron 3 oxide, so on and so forth. Any kind of combination of a metal and a nonmetal. Something that we use the ionic bonding rules with. We're going to refer to those as a formula unit. And you've got some examples there, copper 1 sulfate or sodium chloride. And then the last one on there is just molecules. Covalently bonded groups of atoms. You know, how can we tell if we look at the name of something that it's covalent? Things like carbon monoxide. And that's molecules. So, and the reason we're going through this is, as we get into these conversations about the mole and different things, we don't want to necessarily just use the word particles. It's a little bit too general. Right? This is a specific example of when we're talking about iron. We're talking about atoms of iron. We're talking about sodium chloride. We're talking about formula units, right? 1 sodium and 1 chlorine, ionically bonded together. Or we're talking about ions or whatever. Because as we break down these different pieces and start getting very specific on what we're exactly asking for or talking about or whatever, again, in chemistry, we want to have some precision. We want to be precise about what we're talking about. So I'll give you another minute or so to get this all copied down. Notebook today, BK? All right, so let's practice. So write these down in your notes. We'll do the top ones first. Just jot them down kind of like you see them here and identify what kind of particle each of those represent. You've got your 4 options above you. So lithium bromide, which of the 4 things, right? Atom, ion, formula unit, or molecule, which of those 4 would lithium bromide be considered? All right, so here we go. Lithium bromide, what is it? How do you know? Yeah, metal and a non-metal. I mean, formula unit, FU. I don't know how else to do that. What about sulfate? Where have we seen sulfate before? If we're saying sulfate, where is that identified at? Where have we heard that before? So that would be an ion. Iron 3. This one's kind of tough. Iron 3. Atom? Atom? Who agrees? Who disagrees? Why the 3?
Because it's an isotope? No, I was not sure.
Why the 3? It's a transition element, and we want to know specifically what kind of ion this is. Iron 3 is an ion. If we just had iron, if this just said iron, then we would be talking about elemental iron. Make steel with it or whatever. But as soon as you put a 3 in there in parentheses, what is a 3 in parentheses? A Roman numeral 3 signifying chemistry. A charge, an oxidation number. Right? So if we were to write the formula for this, it would be this, right? So that is an ion. Yes, it's just iron. I agree with you there. If it was just Fe, yes, it would be an atom. We'd be talking about atoms. But as soon as we call it something with Roman numerals and parentheses, now it becomes an ion. What about dinitrogen pentoxide? Why? Yeah, so it's two nonmetals. We can also kind of tell it's covalently bonded, right? Because it's using covalent bonding naming rules here. And again, I might not even remember what di or penta really means, like what the number it means under the hood. But I can see that and I can recognize that these are covalent naming rules. Covalent bonding signifies a molecule, signifies that what kind of particle it is. Chromium 4 oxide. What would we call that? Yeah, formula unit, right? We can tell by the metal and nonmetal. And then lastly, carbon tetrachloride molecule. What about down below? Lead plus 4. How can we tell? Yeah, right? SRS. What would that be? Formula unit, right? Strontium's a metal, sulfur's a nonmetal. SO3. Ion. Why do you think that?
On the back.
So it's on the back. Why? We found sulfate on the back. I found SO3 would be sulfite. No, this is a molecule. Why is this not an ion? What's it missing? Charge. If it said this, now it's an ion. But without that, it's just sulfur trioxide.
So it doesn't so if it doesn't say the charge, okay.
Right?
Like it says on the back.
Correct. So when this has a charge, if this is this, now this is the sulfite ion, polyatomic ion. But if it's just SO3, just like CO2 or H2O, it's just a molecule. We would use covalent naming rules. We would call that sulfur trioxide, right? CO, what's that?
Carbon monoxide.
And what would we consider that?
Molecule.
Molecule. C2H3O2 minus.
Ion.
Why an ion?
It has a negative charge.
Yeah, it's got a charge on it. It must be an ion. What ion is it? Want me to recognize this guy? Acetate. The acetate ion. Just throwing it out there. VBR5.
What's V?
Not vibranium. Close, though. V is vanadium.
Transition metals.
Transition metal. So what would this be?
It would be
Formula unit. Metal and a non-metal, right? What's the name of this? I'm really failing at the U here. What would you call this compound? What would the full, precise name be for this?
vanadium bromide.
Vanadium. 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 No? Somebody said it. Did I not hear it? We'd call it vanadium. Vanadium 5 bromide.
Wow.
Why the 5? How do I know it's a 5?
I
Oh,
don't.
5. Because the subscript.
Yeah. Well, yeah. So if bromine is a 5 here, that must mean that the vanadium here is a +5. We need the 5, the V, in the name of this because it's transition metal, right?
If it's on the right or the staircase thing,
Everybody got this? Move on. Do something more fun. Get these T-charts started.
No, don't go.
the staircase. I'm pretty sure it's like between the. I don't know. I forget. Oh, I know.
Give me the green light, Miranda, when you're done.
Okay, give me 1 second.
Everything on the left is metal. These are transition metals.
I just want to write down the ones that I just wanted to.
Take your time. We're on your schedule at this point. All right, here we go.
Wait.
Left is metal. Right is metal. That's how many.
All right, how am I doing here?
1 second, I'm still writing the title. Yeah, you're doing good. Never mind.
Am I doing okay here?
Yeah.
How can I possibly have 3 things that are equal to each other?
Because they have
Different units, but are they not the same? So if I were to describe a thing, I don't know what. If I had something and I measured it and it is this long, I could say it's 36 inches long, or I could say it's 3 feet long, or I could even say it's 1 yard long, right? Would I be wrong in any of those cases?
No.
No. All 3 of these, we would say, are equivalent. And back when we did T-charts, that was the important part, right? Were things that were equivalent so that we could transfer back and forth. We were talking about 2.54 centimeters equals an inch. 12 inches equals a foot. 5,280 feet equals a mile. And we did conversions with that. And we'd have these big long chains of converting. Okay? So I want you to write this one down, not what I just wrote. And I want you to put it somewhere where you can circle it. You can put asterisks around it, little heart-shaped things, colored pencils. You can go get like a strip of LED lights and install that into your notebook.
I might do that.
I know you might. 1 mole equals 6.02 times 10 to the 23rd particles equals what does MM stand for here? Molar mass. So this is the equivalent of the thing I just had on the board that said an inch or 12, what'd I say? 36 inches equals a yard equals 3 feet. All 3 of these things, for the sake of T-charts and conversions, are the same. We can use any combination of these. If we have a mole of some substance, we have that many grams of it via the molar mass calculations that we did earlier this week. If I have that many grams of that substance, I also have 6.02 times 10 to the 23rd particles of that, whatever it is. Depending on what that substance is, we could use the stuff we just wrote down. We could talk about atoms of a thing, ions of a thing, molecules of a thing, so on and so forth. So all 3 of these, circle this, big text, underline, colored ink, whatever it is, in your notes. This is one of those things that if you get it, will make all the rest of this just that much easier. That you are able to use these equivalencies, these three things that are equal in the T-charts that are to come. Okay, and there will be big T-charts, and this is the core of most of them, is a conversion just like this. Everybody got this? Bold print? Big letters? So let's see if we can do this. Here we are converting again, back from that place that we stuffed them, have returned T-charts. Now, if you're like me, you're super excited about that. Love me some T-charts. Okay, what do we do first?
Make the T-chart.
Make the T-chart. Yeah, let's keep it simple. Okay, so far so good. I remember how to do that. What's next? Write down, not unit, yes units, but write down what here? What we are. What do you always start with in a T-chart? Yeah, what you're given, right? What the problem gives you. So what's the problem give us here? Now, I am going to tell you something now, and I'm going to tell you again and again and again. You're going to hear this 50 times. Some of you, despite hearing it 50 times, will still refuse to do this. And I don't know why. I'm begging you to do this. Just do it. When I talk about units here, I want the whatever it is we're talking about. It is not enough to put 6.4 grams in your T-chart. You have to put what we are talking about. Again, these T-charts are going to get crazy. And you have to be specific. We're talking 6.4 grams of what?
Oxygen.
In this case, oxygen. In any given problem, it's going to be whatever it is, but you need to specify what that is. And trust me, this will get crazy. Yes?
So with like the oxygen, do we just, because it's a diatomic, we automatically put it in there as O2?
Again, that's yes. As soon as you see oxygen, we're just talking about oxygen, it's going to be O2. Lubin, what was your question?
How do you weigh oxygen?
With a scale. How does anybody else weigh oxygen?
Yeah, but like oxygen is like all around. Like, how do you weigh it? If I put it on the scale, it doesn't read anything. You can't like hold oxygen.
What do we do? What we're going to actually do is measure the volume and the temperature and the pressure. But for now, we're just going to talk about grams. So you're right. There is a challenge there on how do you measure a thing that's a gas. For now, we're just going to worry about there is an amount of oxygen, right? So in this room, there's some number of grams of oxygen. Okay, weighing that would be difficult, sure, but for the sake of right now, just stay with me. Believe it or not, we're going to get into conversions where we can convert grams of something into liters of something.
Can we not just multiply 6.4 by 2? Get rid of that.
We'll get to that. All right, so what do we copy down in a T-chart? What's next?
Put grams on the bottom. What are we converting to?
So again, in a T-chart, you copy down diagonally your units.
We put 1 mole above that.
Well, so we're going to go to moles, right? Our conversion, we have that big thing you circled and highlighted in your page. We can go to moles of O2.
1 gram equals 1 mole.
Nope.
Oh, then you lied.
So hold on. So
Find the molar mass.
1 mole of something equals 6.02 times 10 to the 23rd particles of something equals the molar mass of something. So now let's go back. Oh, deleted. Dang it. Let's see if I remember what we had up here.
We literally got 6.4 grams O2.
So how do we calculate the numbers for here? What did we do earlier this week? What did you do in the investigate yesterday?
Find
Find the molar mass of what? O2. How do we calculate that?
It's 16 grams.
O2 of them times 16. O2. There are 2 oxygens. We have to count them, just like we did earlier this week. You need to multiply the average atomic mass times the quantity. You get, obviously in this case, we're talking about O2. So we have our molar mass, right, of O2 is 32 grams per mole. So what numbers can we put up here?
So 32 on the bottom and 1 on top.
32 grams per 1 mole of O2.
Yeah, cuh.
What's left to do here?
Now you gotta divide.
Your calculator. Now we just do the math on the T-chart. 6.4 divided by 32. So this is what you did in the Investigate yesterday. This is just like the T-charts of old. The units are a little different. The conversions are a little different. But the general format of a T-chart remains the same. And we have this box, right? We have our vertical components in a T-chart that are just 2 equal things bent.
So if you had like a compound, you would put the compound in the same box as where O2 is in.
Hold on tight. Coming soon to a theater near you. Everybody got this? This T-chart and this math? Ooh, gonna get rid of that. In your papers, try this one. Try and at least set this up. I will give you a few moments to try and set up this question. You all know how to do this. How many grams of iron 2 phosphate are in 1.25 moles of iron 2 phosphate? I'll give you a hint. You got to start with one of these. Is that enough of a hint?
Yes, sir.
No. It's not enough.
No.
There's almost like more than one number.
Oh, it's iron phosphate. I forgot the phosphate.
I got the class too. I thought I could. I got the iron. Very proud.
Did I do them separately?
No.
Your T-chart should look like this on the board. Now, there's still some work to do, but your fundamental what goes where should look like this.
What do you mean times 8?
Yeah, I only did 9.
So, cute and friendly. This is not cute and friendly? Yeah, it should. It should.
You're gonna lose the fight.
Wait till you see where we're going with T-charts. And you're going to look back on this fondly. Boys, you're going to look back on this and be like, would that we could go back to this day. All right, so how do I continue from here? What is missing? What do I need?
Divide by 610.
I need molar mass, right? So how do we find the molar mass of this compound?
Add them together. So you take the 56 and you add phosphate.
3 is 2, 8.
I figured out how many grams are in 1.5 moles of iron.
So you need to do this math. The molar math. Molar mass math. 357-ish. You got 358, it's fine. 357.4 is what I got. Whatever, it's close enough. Technically not, but it's close enough. If you got 40 something, not right. If you got 143, not right. If you rounded, however you rounded this, the whole numbers are close to it, you should get around that number. But again, this is where the molar mass comes into use, right? Because now we have an equivalent. Remember, what's our unit? When you do all this stuff, what was our unit down here? Grams per mole of a substance. Grams per mole. Grams equals 1 mole, whatever this grams is. Now this is always going to change. Whatever you have here has some molar mass. Right? In the slide before this, we had oxygen, which had a molar mass of 32. Now we have iron 2 phosphate. It has a molar mass of 357. And now what do we do?
Multiply.
Yeah, just the math.
Mr. Clymer, is there any error, like leniency for error on like tests and stuff? Since some of our like weights are different, like the atomic weight, atomic mass.
Again, if your answer was something close to this, and by close I mean within a gram or two, I'm going to be okay as long as your setup is fine.
Okay.
And I know, like, what I'm looking at, the numbers on that periodic table are different than our yellow periodic table. For tests and quizzes, I will be basing my numbers on the same periodic table you all have in front of you.
But we all have different.
We got different ones.
Okay, so we'll have to update the periodic tables. But ultimately, none of those are going to be so far off that I'm going to see 445.8 and mark you wrong. No. 302, I'm going to question something's happening inside your T-chart. Okay? Everybody got this? Everybody figure out how we got here? All right, let's keep going. Not yet time to call Uncle.
Uncle who? Unky? Where's Unky at?
Here we go again. We are not yet done. I know what the first step is.
Where's my Unky at?
What do I copy next? What am I trying to get to? Nope. Atoms of carbon. Where do I have a conversion between atoms of something and moles of something? Nope. Do we? Hold on, that's a good question. Do we need, looking at this, do we need the molar mass of carbon for this problem? No. Right? Particles is what we're looking for. In this case, atoms, because we're just talking about carbon. What conversion do we have? Look above you in your notes that goes from particles of something to moles of something. Get out your calculators.
Wait, so you don't like solve.
That's all. You don't need to, right? Look at this.
I do not get this L.
We have a mole to this. All we're doing is this part of this thing. It's just a T-chart.
I'm gonna just start crying.
Yes. Okay, so once you have this set up, next is how do I do this in my calculator? On a TI-8485 graphing calculator, to do this math, now you're going to want to follow me here, on your calculator is 12 times, to put this into your calculator, you would type in 6.02 and the EE button. On my calculator, it's the second button, the blue button, and then the comma. And then EE23. The EE in your calculator stands for times 10 to the, then you put in a number.
Wait, so do we have to put times E or can we just put
No, you just put E. So in your calculator, you will type 6.02, then the E, then 23 for this number. And then enter. If you do not have a calculator like this, okay, if you forgot it, that's one thing. If you don't have one of these, you're going to need to borrow one of these non-scientific calculators, but at least I know how to use this. If you're trying to do this on your phone, it's entirely possible you're going to have a bad time. I don't know how to do this on every kind of phone and every kind of calculator. But I know how to do it here. So show me on your calculator that you know what I'm talking about.